Hello everyone and welcome back to the channel. Today I just want to do a short video based on the levelized cost of storage video that I did last. So here I have the model that we built together in the last video, and if you follow the links that I gave to you in the description of that video, you can see that you can purchase the levelized cost of storage by coming to the website on this link above here and clicking on the battery standalone BESS system. But you can see here in the web page that I have a few other models, all levelized of cost of electricity. And I would like to discuss with you guys today the one that has the solar, wind, battery, and diesel system, and see how complicated these calculations can be, right? So if you take the time and click on the live preview, we're going to be able to see what the model looks like. So if you go over here and click in calculation, we're going to see that most of the model comes about like calculating LCOE. I'm going to close this and I'm going to open the real file, which is over here. So you can see also when you see the live preview, Google Sheets doesn't really show it perfectly, but in Excel it's going to look like this. And if you scroll down over here, you can see that mostly half of the rows of this model is with regards to the calculation of LCOEs. And I'm going to go through the steps and explain why this is the case. Okay. But before we go there, please make sure to subscribe to the channel, give me a thumbs up if you learned anything from today's videos, and hit the bell so you can get to know whenever I release a new video. So let's see first what we did in the levelized cost of storage video. I put together a very simple diagram, which is this one here. And basically in that particular model, what do we have? We have a grid where we have a cost for charging the batteries, and then we just discharge it. And we calculate the cost of discharging the battery, or the levelized cost of storage, because that is what we're calculating in the first model. We're calculating how much it's going to cost us to discharge this electricity from the battery. And if we're going to get paid is higher than the LCOS, then your model would be, we would have a sound business case. But today what I want to do, I want to show to you exactly what we have in this model over here, which is a solar, wind, battery, and diesel system. And if you look what the diagram should look like, would be something like this. So basically, we no longer have the grid in this particular model. What we have a load. A load being a factory or a commercial or industrial, whatever. It can be anything that needs electricity. And what we're going to have the wind farm or the wind turbine feeding directly to the load. We're going to have the solar panels also feeding to the load, and both of them are going to be feeding electricity to charge the battery, right? Then the battery is going to discharge everything to the load, and as a backup system we're going to have the diesel generator over here, which is going to go directly to the load. It doesn't make sense to charge the diesel to the battery because first it can be quite expensive, and of course you can control how much energy you are producing from the generator, right? And because we're constrained on how much electricity the load can take, there's a maximum demand the load is going to be able to take. There might be periods of time where we're going to have to curtail your renewable generation, and that's going to be the case for the PV and for the wind. So there's going to be some curtailment over here. All right, so this is the setup of our model, and now we need to come up with the calculations of the LCOE, or what I call in the model the blended LCOE. So how do we go about it? Let's gonna go a step back and go back to the LCOS. And if you have watched the video, and I recommend you to click on the link below and watch it, you will remember that there's a point when you calculate the LCOS, and I just ask you guys which flow of energy we should consider in order to calculate the LCOS. And I'm gonna go to the model now. I have it open over here. And if you recall, here is where we calculate the LCOS. And the LCOS is the sum of the capex and opex. So we have the capex on cell H23 and the opex on cell H31. All right. And then we divide by the NPV of the energy discharged, right? But by the time when I was doing the video, I asked you which one of the two rows, let me do it again. Which one of the two NPVs we should consider? Should we consider the 25 or the 31,000 megawatt hour? And the answer is that we need to consider the discharge, right? The output energy back to the grid. And that's going to be the same principle over here. The energy flow that we need to consider is always the one that is being to the load, okay? And we can get lost because we have several energy flows going, right? So we have the energy flow from the wind turbine to the battery, the same from the PV to the battery. And when we're doing the calculations, can get really lost, okay? Another thing that we're gonna do when we have such like a hybrid system, a big system like this, is to calculate each one of the LCOEs individually, right? So we can calculate the LCOE for the diesel, we can calculate the LCOE for the solar PV, for the wind farm, and of course for the battery, right? And then we're gonna have an idea which one is cheaper, and you can really make a deeper analysis and understand how our system is working all together, okay? And that's the purpose of the video. So let's see how to do it right now. All right, so I'm back here to the model, okay? The purpose of the video is not to build this model from scratch. So basically I'm gonna do a quick walk through the model. And from here, we're gonna see how we can calculate each one of the LCOEs, all right? So as always, we have a results sheet where I'm basically presenting each one of the values for the LCOE. And you can see already that we have 2 results for each one of the sources, plus the blended LCOE. So we have including the curtailment and excluding the curtailment. And I'm going to explain to you why you also have to calculate both of them. We have some graphs, the battery efficiency, and we have the LCOE breakdown by capex and opex. Here we have the input sheet. So let's see what we have in here. So we have some data to come up with our time series with the construction operations period. Then we have the inputs for the generation, and you can see we break it down into PV, wind, diesel, and the generation from the battery system to the load. So this is a given number, okay? And for each one of the renewable sources, we have the stream of energy from the renewable, in this case PV, to the battery. Then we have the flow of energy from the PV to the load, and then we have the curtailment. So going back to the diagram, so all these energy flows here are given, right? So all of them is given, and all these energy flows are inputs to the model. Everything here is basically an input to the model, okay? So that's it. Then we have the costs, the capex and opex for each one of the source of or equipment, okay? So we have PV, wind, diesel, and for diesel we have fixed and variable costs. We also have for the battery, all right, which are the same ones that we used in the previous video. And I also added in here a other cost. And if you go to our diagram here, that represents the other cost, okay? It can be a grid connection, can be your controller to monitor and control all the systems here, can be a lot of things, okay? Which is being represented by this icon over here. And this is going to add some other complex to your case into the LCOE because there is no energy flow, it's just a cost. So basically, how do you spread this cost to your LCOE calculation? All right. Okay, and then we have just the discount rate over here. So that's our inputs. I'm going to go to the calculation sheet now. So we have the same structure as for the LCOS model. Then what I modeled here, it is basically the energy flows, right? So we have the energy flows. Let me just gonna zoom in. So we have the energy flows from the PV to BS, PV to load, and PV curtailed. The same inputs for the wind, and for the generation or for the diesel generator, we only have the. We also have here. Sorry, we also have here a flow from the diesel generator to the BS. Okay, that's I left in here, but very unlikely that are gonna need it. Okay, or in a real case situation. So this flow is also considered in here. But what we don't have for sure is the curtailment. Okay, you will never curtail your generator. That's doesn't make any sense. Even this one here, we can say, look, we will never charge your battery with diesel, right? Okay, then I calculate here how much generation goes from the. And I actually don't calculate. We bring the values for the generation from the battery to the load. And then here I calculate the total generation, which I'm just adding all these numbers together. All right, so this is the total generation to load. and total generation, which is just adding everything together. Then basically here I lay out the numbers in the timeline series, and then I calculate the NPV for each and every row of cost and generation, right? In this case, only for the generation. I'm going to calculate the costs over here. Okay, so then we have the capex. We have capex for PV, wind, diesel, the batteries, and the others. So you can see the 100K USD is over here, is spread evenly in our construction timeline. And then I come back here with the total NPV for this project, right? Now we come up with the opex. We have fixed opex for the PV, wind, diesel, PS, and other. And just pay attention here, just added like fixed PV for the source of generation, okay? Except for the diesel, where we have the diesel variable cost, because that's the fuel, right? So I think you can get by in the model only having fixed cost for the PV, wind, and battery, but for sure you need a variable cost for the diesel, because that's the majority of the cost for the diesel generation. Okay, cool. So again, I lay out all the costs in the time series, then I NPV everything over here. All right, and now because we have all the NPVs for all the energy flows, plus for the capex and plus for the opex, what we can do now, we can start calculating the LCOE. And in this model here, what I start doing, I first calculate the LCOE for the generation asset, okay? And we have the PV, the wind, and the diesel. And as explained before, I calculate 2 LCOEs for each one of them. I calculate the LCOE including the curtailment and excluding the curtailment, okay? So why do I do it? Let's go back to the diagram. So we are assuming here that we are feeding the electricity to a load and there's some curtailment. So the reason for me to calculate or to consider that this curtailment here is going to go to the load sometime soon is that eventually we might find some use for this electricity, okay? And I want to know by how much I want to be able to reduce my LCOE if I were able to find use for this electricity that is being curtailed. So that's the only reason why I calculate it. But what really matters for my model is the LCOE excluding the curtailment, because that's the real use of energy that I will have, okay? So how do we go about to calculate the LCOE including and excluding the curtailment? I'm going to press F2 in the PV calculation, and you can see that what I'm considering here, I'm getting the capex for the PV only and the opex, and I'm dividing it by the NPV of what? Total generation, okay? So in here, I'm including the curtailed electricity produced as part of the LCOE, and that's why this is the LCOE including curtailment, okay? So let's go to press F2 again. You can see that I have the capex, the NPV of the capex, the NPV of the opex, and I'm dividing it by the NPV of the total generation by the PV asset, okay? Considering everything, all right? So that's the cost, the LCOE for the PV. And if I were to exclude the curtailment, the only thing I have to do, I have to change the NPV of the generation, which is now only considering the generation from the PV to the battery, plus the generation from PV to load. Okay, that's it. So from the perspective of the PV asset, okay, from this perspective here, the LCOE produced by this asset here, excluding the curtailment, we have a total cost of 51.87. I do the same for the wind. The only reason why the numbers are the same here is because I'm using the same inputs, okay, but of course that's not going to be the case. But they just produce the same results, of course, if you get the same inputs. All right, it's the same principle, the same calculation, nothing changes. And for the diesel, we have the same numbers, just because there is no curtailment, right? So there's nothing being curtailed over here. But I do have, let me just add here, I do have a generation come over here. Okay, so this is the correct diagram here. Let me just move this. It's gonna put here in here. Okay, so that's how it should look like. Okay, so we also have over here. Okay, cool. So what I'm gonna calculate next? Okay, next I am going to calculate. Oh, sorry. Let's gonna get back here. one important thing. As you can read here, I'm calculating the LCOE excluding the battery and other costs, okay? So I'm not considering the capex of the other costs, which is in this row here, neither the opex, okay? None of them is being considered, okay? So this is the LCOE only for the PV asset, only for the wind asset, and only for the diesel asset. All right? Cool. Now we're going to calculate the LCOS only for the battery. And the first thing I do here is to calculate the LCOS for the capex and opex excluding charge costs, okay? So let's give a think here. So every single battery has basically three main components to calculate the LCOS, or the levelized cost of storage. We have the capex, the opex, and another thing that we have to consider always is the cost for charging the battery. There's a cost for you. It may be zero in some circumstance, but most likely will never ever be zero, okay? So that's what I'm calculating here now. It is only the LCOS excluding charging costs, or the LCOS of the considering the capex and the opex. And that's very straightforward to do. For the NPV of the costs, I have the NPV of the capex and the NPV of the opex, and I'm dividing by what? I am dividing by the NPV of this energy flow over here, okay? The NPV from the battery to the load. And if I press F2 here, it's H33, which is this flow over here, okay? So that's the LCOS excluding the charging costs, okay? What I have to calculate next is the battery efficiency. That's important because that's going to tell us how much is going to be the cost to charge the battery, right? So we know already how much the LCOS is without the charging costs. So what we have to come up with now is the charging costs. So how does it work? Let's go back to the input sheet, and what we have that we're going to feed the battery, or the battery is going to provide 10,000 megawatt hour per year to the load, and it's going to be fed, the battery is going to be fed with 4.5 thousand coming from the PV, an extra 4.5 thousand coming from the wind generator, and another 4.5 thousand coming from the diesel generator, okay? So if you calculate the efficiency, which I have over here, that's going to give us a 0.74%. which is the same number we have down over here, okay? So that's the efficiency of the battery, how much energy we are taking in and how much energy we're taking out, all right? So this calculation here presents the percentage of the energy, sorry, let me just change this to this number. So this number presents the percentage of the energy that is coming from each one of the generation assets, okay? So because we have an even number coming from each one of them, of course, the total percentage is going to be divided by 3. And if we were to have, let's say, 0, then we would have 50-50, okay? So that's what it represents here. I'm just going to press Ctrl-Z and come back here. And why do I need it? I need it to calculate I'm just going to add one row here, to calculate the LCOS charging costs, okay? And I have the formula here ready. So the charging cost for this battery is going to be should be equals to this formula over here. Okay, it's going to be $115. Let's going to break this formula down. So basically what I'm getting here, I'm getting the average cost of the LCOE coming from each one of the generation assets and dividing by the efficiency of the battery. So that's the cost for us to charge the battery, right? So I'm getting how much energy I'm going to be feeding in, okay, divided by the efficiency of the battery. So that's how you calculate the charging cost, all right? So that's what I'm calculating here. And of course, we can also calculate the charging costs without excluding the curtailment, which is going to be, let me just copy the formula over here. Copy, I'm going to just paste over here, and then we just have to move this one over here. And that's going to be the calculating the LCOS excluding the curtailment, okay? And excluding the other costs, which if I make this a bit bigger, you can see that's exactly what I have. So we're including the charging costs and excluding the other costs. And here we are, let me just fix over here, excluding the curtailment and excluding the charging costs. Okay, so if we add together now the LCOS excluding the charging costs plus the charging costs, we're going to get the LCOS for the battery, okay, for the storage system. And that's what we are calculating over here. So far we have basically 8 different calculations for the LCOE. Now I finally come to the point where I'm going to calculate the blended LCOE. And remember, by blended, I mean the LCOE that is received by the load. Okay, so what is the LCOE? Let's say that the load is seen, okay, that's perceived by the load. So how do we do it? Well, that's quite straightforward, right? So I put here 2 different ways to calculate it, okay? And for this calculation here, the second method we only work for without considering the other costs, okay? And I'm going to show to you why, and that's exactly what I'm putting here. So this is the calculation without considering the extra or the other costs, right? So the first way is pretty straightforward. We're going to get all the capex, excluding the capex for the other costs, all the opex, and exclude the other costs. We're going to NPV them and divide by the total generation received by the load. Okay, so we're going to get these 4 streams here, NPV them, and get this number, get the NPV of the capex and opex, and divide by this number. I'm going to go over here. I'm going to press F2. Let's see what we have. So I'm getting first the total capex, and I'm subtracting what? The other costs. Other costs are not part of this. And I'm doing the same for the opex. I'm getting the total opex and subtracting the other costs. All right, so that's exactly what we discussed here. I'm getting all the costs, all the opex, minus the opex and capex for the other costs, which is this cost over here. Cool. And we are dividing by what? We're dividing by all the energy flows going to the load. So we have 4 here. Let's go see why we have only 3 here. I'm going to go up. So I have the total generation to the load, okay? And actually because I have total generation to the load, I'm just now subtracting. Oh, this is including curtailment, right? So I'm getting the total generation to the load, right, which I already have, which is the 4 arrows over here. And I'm just adding now what has been curtailed, okay? So that's how I'm calculating here the blended LCOE including curtailment. And for excluding curtailment, basically what I'm going to do, we have the same thing for the NPV of the costs. Okay, so it's the same formula, doesn't change anything. If you follow here, you can see nothing changed. So I have the first one here and the second one. You see nothing changes. All right. And then what are we dividing by? We're dividing by the H35. So let's see what the H35 is. Total generation to load. Okay, so pretty straightforward, right? So what is the second method? So this is a bit more complex, as you can see on the formula. Okay, I usually calculate like this because the formula is much simpler. But if I were to be doing this calculation on my own, okay, I think that's a much easier way to understand what's being calculated here. Okay, so what I have here. So basically what we have, I have the LCOE of the load. So I have the weighted or the sum of product for, let's say, I have the weighted cost for each one of the source of energy generation to the load. Okay, so I have the levelized cost of the PV multiplied by the total energy provided by the PV, including curtailment. Then I have the, the LCOE for the wind multiplied by the energy provided by the wind asset. And then I have to the load, including curtailment. And then I have the diesel, the same thing. I get the diesel and I multiply that by the diesel generation over here. Okay. And the same for the batteries. We get the batteries, the LCOS for the batteries, and I multiply the flow from the battery to the load. okay? And then basically we're going to divide everything by the sum of all the energy flows, okay? So it's a weighted average cost. And if you do this for both, okay, for the second one too, you can see here I have the excluding cost for the PV multiplied only for the PV generation to load, and I will have then the same calculation for the wind, the same calculation for the diesel, and the same calculation for the battery, and I divide by the energy flows, right? And if you do like this, the results are going to be the same, okay? There's two ways you can calculate, and you can check whether your calculations are right or wrong, and they both should work. And you can see here that this is still not considering the costs, the other costs. Well, next I'm going to calculate the blended LCOE, including other costs. That's what I'm doing here now. And to do it, now the assumption is that I'm just getting, okay, what is the total cost, capex, total opex, I NPV them, and I divide by the load, the energy flows to the load, include and excluding the curtailment. And that's what I have here. So we have the total capex and opex, which is the very last row of each one of the subsections of the model, and I will divide it by the flows, right? The flows from generation to load plus curtailment from PV and wind. And for the next one, the only difference, if you look on the formula over here, you can see that the only difference is, if I go up and down, is that I'm on the second one, I'm not considering the curtailed values. That's it, okay? Then you can see the difference that we have when we add the other costs. So there's a difference of 7,343 minus 7,326, 70 cents. So the 100K, sorry, where is it? It's gonna be over here. So this cost here as a capex and this one here as an opex is adding, let's gonna be here, is adding 17 cents to my cost of energy, okay, or electricity, all right? So let's gonna recap where we are right now. So first, I calculate individual LCOEs for each one of the technologies, including and excluding the curtailment. Then I calculate the LCOS, including and excluding the charging costs. Then I calculated the blended LCOE, including and excluding the charging costs and excluding the other costs of my methodology. And now I calculate the blended LCOE, including all the costs, basically, right? But again, I make the distinction between including and excluding curtailment. If you're sure not going to be ever able to use your curtailed energy, you can just get rid of all these calculations over here. It doesn't matter them to you, okay? You will only consider it to see what is the impact of your curtailment, right? So it's quite significant, right? So if you do want to, it's like 4 cents. It's quite a lot. It's like 5%. If you consider everything, it's going to be 5%. It's quite a lot. So that's why you should do it and see how much you're curtailing, and then you can play around with designs and size of each one of the technologies to really try to optimize your LCOE. All right. And lastly, what you're going to have here, you're going to have the breakdowns. Okay. And again, the only difference between the two breakdowns between this and this is that the second one is excluding the curtailment. Okay. So I'm just going to go through the very last one because the calculations are pretty much the same. So now what I'm getting here for the PV, I'm getting, forget about if error, it's just if this technology has 0 as an input, I'm getting the capex of the PV and dividing by the generation from the PV over here. So let's see, the PV to the battery and to the load. All right. And this is the NPV of the capex. So that's for, I'm breaking now for the capex. For the opex, I have the same denominator, but the numerator is different. So here's going to be the opex. All right. And here we have the energy flows. Okay. I do the same for every single other technology, right? And for the blended one, now that's including the costs, right? The charging costs. So as you can see here, get the capex with everything now, okay? And I divide by the total generation to the load, right? So that's the capex. and here we have the opex. So these costs here include the cost of this other infrastructure in the model. All right. And the only thing that I do differently here, I calculated the charging cost for the battery, as you can see, right? So you can see what the charging cost is for the battery. It's just broken down over here, right? So that's basically what we do. And then I just bring the results over here, and you can see that everything fits correctly and correctly in the results table. Okay, so that's it. Whenever you have this hybrid system, it can get a little bit complicated on how you calculate these energy flows. Okay, you can spend some time and until you get it right, but that's basically considerations we have to have. Okay, so make sure you always pick up the correct energy flow. I think that's where the problem is going to be, and make sure that like when you should account for these extra costs. Okay, another thing just to finalize the video here that we can do also is basically to split the cost of this infrastructure here evenly or proportionally to each one of the other capex. That can be another approach too. Okay, I don't really mind. I just want to show in this way so you can see what the impact can be on your modeling. All right, so thanks for watching. I look forward to see you in the next one, and please subscribe to the channel, and yeah, have a nice evening. Cheers, bye.